Welcome to our seminar. Our today's guest is Christoph Kirsch, who will talk about quantum advantage for all.
Thanks a lot. Thanks a lot for the opportunity to speak here. I just want to say a few words about why I'm sitting even more comfortably than you. I have actually a health condition. I have an injury in my neck, and it makes it hard for me to coordinate and do other things at the same time. So sitting makes it a little bit easier for me. And when I stop sometimes and don't continue doing it, it's not because I don't know what I'm talking about, but it's actually because I have to, my brain has to settle down again. Okay, my name is Christoph Kirsch. I'm a full professor in Salzburg in Austria. I've been there for a long time. But for 2 years, I've also been sharing my time here at CTU and Salzburg, going back and forth all the time. And about half a year ago, we hired Stephanie right there as an intern from Peru. She has a bachelor's degree, 5-year bachelor's degree in computer science, and she actually introduced me to quantum computing about half a year ago, and it was difficult for her and for me, because I was like so many other of my colleagues, like, don't even talk to me about quantum computing. I'm too old, I don't want to hear about it, it will change everything that I learned in the last 30 years, it's too difficult, I have 10 years until retirement, I don't want to do it anymore, it's for young people. And she actually, this didn't discourage her, and she kept talking to me about it. And eventually, after a few weeks, I suddenly kind of understood at least some of it, what's going on. And I was unbelievably surprised how unbelievably simple this stuff actually is. So there's this enormous pile of math, right? And lots of papers about quantum computing, which is completely inaccessible, at least to me. I can read this stuff and so on, but I don't really understand. It's very complex, especially two different kinds of models. Today I only talk about these two different kinds. There's the classical quantum computer model, which is called the gate model. I don't know if you heard about this. I'll just call it GM. So not General Motors, but actually the gate model. Universal quantum computer model, can do anything that a Turing-complete machine can do. Okay? And then I will also be talking about a different model called quantum annealers. Quantum annealers. QA, as in question and answer. And these annealers, they're also quantum machines, but they are simpler, a lot simpler than gate model. They are so simple it's almost embarrassing. They have one drawback: they are not universal. Okay, so they can only solve, let's say, optimization problems. And I understand that there's people here who are interested in optimization, right? So that's the thing for you. Okay, quantum annealers in particular. But anything that a quantum annealer can do can also be done by a gate model, right? Because it's universal. Okay. Now, the thing is here, you won't learn today too much about these two different models, okay? Because I have no clue really, right? I'm just like everybody else, okay? There's a few things that I learned, like this thing. Like, we are computer scientists, right? So the thing that I care about is, what's the programming model of this thing? How do I program this thing, right? That's what I want to know. And then next question is, once I figure that out, how fast can I do it, right? And how much space do I need? How many bits? That kind of stuff, right? But when you read the introductions to these machine models, you don't see the programming model. I mean, they say it's a programming model, but it's mathematicians, right? So they have a different idea of what that actually is. So the programming model of these quantum annealers, at least for me, is actually quite cute. It's simple. It's actually just a so-called QUBO. Anybody heard about this thing? QUBOs? Do you know what a QUBO is? It's not bad if you don't know, because I didn't know until half a year ago. Okay, so Cubo? No? It's I don't even remember what it stands for.
Quadratic
yes,
unconstrained binary optimization.
Exactly. Quadratic functions, okay? Quadratic, unconstrained, so no funny business. Binary, all the variables are binary. Optimization model, problem, whatever you want to call it. Okay? So this thing, a cubo, is a binary quadratic function. Okay? So what you got is like this. You can have x times x. You can have x times y. And you can have, I guess you can have x, and you can have y, and you can have a constant factor. Okay? That's the kind of thing. That's a cubo. Okay? And you can actually get rid of this guy here, because it's binary variables, right? So who cares about that guy? Right? So actually the name quadratic is a misnomer. These are actually bilinear functions, right? So this funny thing here is called a bilinear factor, right? And this is a linear factor. Okay, that's it. Okay, so that is the programming model of this class of machines. So if you can express your problem in this cubo function, you can run it and solve it in principle on a quantum annealer. Okay? Now, why is that? It's incredibly simple. It's like this. So this is my quantum annealer. Okay. And let's say it has quantum bits, right? Let's say it has 9 quantum bits. Okay, it's a small machine. The latest model has about 5,000. So just in case this confuses you, the gate model machines, they are like, we are at 100 maybe, at most, okay? But with quantum annealers, they scale to, factor 10, 5,000 right now. I think they announced 7,000 machine, and it grows, okay? And that's because these machines are much easier to make, okay? Now, that's because the following. So let's say we have a 9 quantum bit machine, a quantum annealer. Then the only thing you can say, the only programming concept you have for this thing is you can say for each bit, it's so-called bias. Yeah. So is it biased towards the value 1 or the value 0? Okay. I mean, it's these probabilities, right? Each quantum bit can be in both states at the same time, and you can shift the probability towards 0 or towards 1. Okay, that's your one programming thing. And how do you do that? Well, very simple. It's the linear factor way you do this, right? So this guy here, this variable x, represents exactly 1 quantum bit, yeah? And you put a factor on, in front of it, some constant factor, yeah? And that's your bias. And it's between, I don't know, I mean, you have to normalize it, and that's it, okay? The other thing you can do is, you can do this for all these quantum bits, right? So you will have, in this case, 9 variables, okay? And then the other thing you can do is, you can entangle these guys, 2. Any 2, you can entangle them and talk about, what is the chances that they have the same value or the opposite value? Well, I guess you can easily see that this is expressed using these bilinear factors, okay? And that's all there is. Now, how do you run this program? So suppose you came up with this. So you want to solve your fancy optimization problem. Yeah. First you have to squeeze it into such a function. And then you set this function to 0. And then the question, the problem that you're trying to solve is which assignment of variables, again, just binary variables, yeah, makes this true. Okay, and you can do this in such a way that the function is always, evaluates to a positive value or 0. It doesn't go negative. I mean, there's different ways of doing this, but this is a simple way of doing it. Okay, so that's the question you ask. Now, how does the quantum annealer help you with that? I mean, this question, if you try to find an assignment, whether it even exists, yeah, an assignment of variables such that this thing becomes zero, is an NP-hard problem. Okay, it's equivalent to SAT, right? So for people who haven't heard about this stuff. So this is an NP-hard problem already, can do as much as SAT can do. Yeah, and that's nice. Okay. Now, when you put this on your quantum annealer, then these people that make these machines, they tell you that with high probability, in constant time, this damn thing gives you the variable assignment. In constant time. Okay, we are talking 20 microseconds or something. I think that's the number. Now, if the probability is not good enough for you, you just run the experiment again and again. What is physically going on here is very simple. Yeah, and we wrote this paper, Stephanie and I together, and I dared to put a paragraph in on quantum annealing, and I described it as follows. Do you know what a shaman is? These guys, you know, that have bones and feathers and stuff, and they throw them on the ground, and then they read the future from that stuff. Yeah, that's what a quantum annealer is, except that I can program some of the physical properties of these bones that I'm throwing. That's what it is. Yeah, it's fascinating. So these quantum bits, they are in an entangled situation here that I programmed, and now I put power on them, and the energy level rises, yeah, in the system. So that's the process of throwing them on the ground, the bones, yeah. And then I shut off the power and I let the power go down, the energy level go down in the system. The whole thing takes 20 microseconds, and then I read from the system where it ended up. And if the energy level is a low energy level, whatever that means, then there is a solution to this thing that's equivalent to that it evaluates to zero. Okay? That's what it does. And if you repeat this process and it always ends up, it stays in a high energy state, then the chances are high that this thing doesn't have a solution. Okay? And if it has a solution, it comes to a low energy state, and then you can even read the value of the variables that will give you a solution. Okay. Now, don't get too excited about this. I was so naive in the beginning. I thought that we are done, right? This will solve NP-hard problems. You just have to make the machine big enough, and once and for all our problems will be solved. Yeah, but that unfortunately is not true. Okay, and here's the problem with this: is that no one actually knows whether this thing is going to give you that assignment, if it exists, so that it solves the function for all possible functions. So there might be functions where the quantum annealer will fail to find the solution even though it exists. Okay, and that's why that's because these entanglement effects here and so on, you know, they are not perfect. There's problems where the system might get stuck in a non-global minimum, in a local minimum somewhere, and it cannot reach the overall global minimum of the energy minimum of the system. Okay, and there's an ongoing debate about this. Okay, so these machines, there's no proof that these machines can actually solve all possible functions. Okay, and there's already some papers about, you know, where they try to have a quantum annealer solve subproblems that are extremely hard to solve classically, and the quantum machine also fails, also struggles with these subnets. Okay, so we are all good, right? We will not be unemployed in the future. Okay, so there's still a lot of work to do. Okay, any questions so far about this? Okay, Now, the gate model machine here, on the other hand, right, is very different. It's a very different animal. And Stephanie and I are currently trying to understand it, and we are studying it and so on, but I can't really talk about it today. It's too early, okay? But it doesn't matter for our talk here. It's good enough to know this thing, yeah? So now for the rest of the time, I have the following two goals, okay? What I want to do is, I want to show you two things. I want to show you how you can actually run virtually any C program. Yeah, now we are back in the classical world. Any C program on this model, on a quantum annealer. Okay? And secondly, I'm going to argue then how we can utilize this idea to define a quantitative notion of quantum advantage. Okay, so it used to be called quantum supremacy, but it got described as politically incorrect. So now everyone calls it quantum advantage. We are modern, I call it quantum advantage, whatever. The thing is, quantum advantage so far only has the following sort of 0-1 definition, yeah? So it says something like, you have quantum advantage if you can solve a problem on a quantum machine that you cannot solve classically, whatever that means, yeah? Okay, so with this construction that I'm going to show today, we can define something like, how much quantum advantage do you actually have given a number of quantum bits on the machine and given speed on the classical side, right? Because I can make my classical side faster and faster using all kinds of tricks. And as long as I can do that, I make it harder for gaining quantum advantage, right? So it actually is a concept. It's something where you trade off classical side and quantum side. And actually, honestly, these days, there is no quantum advantage for almost anything. Yeah, it's very hard to actually show that. So I'm going to argue about that as hopefully if I have enough time. Okay. So how do we run any C program? You give me any C program, and I tell you what it's allowed to do. It's allowed to have procedures. It's allowed to have arithmetic. It's allowed to have if conditions, while loops. It's allowed to have recursion. So there's dynamic allocation of memory on the stack. And it's even allowed to do malloc and free, dynamic allocation of heap memory. All of that, how do we get this into this kind of, that's almost like a straitjacket, right? I mean, it's like, there's no room whatsoever. I mean, you just have these binary functions. How do you do that? Yeah. Anybody here who would maybe has an idea? And Stephanie was talking to me like for weeks, right? And then I understood this model, and then I thought, oh, maybe we can do something. We can do something with a notion called symbolic execution. Okay. Anybody heard about symbolic execution here? No? Okay. You heard about it. Yeah, I was bothering you with this already a lot. So there's this concept of symbolic execution. So this thing is really awesome by itself. Yeah, it's completely independent of quantum computing. Yeah. So what is symbolic execution in a nutshell? So suppose you give me a binary. Yeah, I'm not talking about high source code. Yeah, just a machine binary. Yeah. Now I want to execute this, so I let it run on a machine or a simulator, emulator, doesn't matter. Yeah. And what you are all used to is you run it on concrete input. Yeah. So you feed it some input and then you see what happens. Yeah. Now, symbolic execution is the same thing, except that you run the code, really just the machine code, for all possible inputs at the same time. Okay? So as it consumes more input, it reads input from whatever network, I don't know, consoler, yeah? The execution is done in such a way that it does not actually specify the input concretely, but it maintains it symbolically. Okay, it's awesome. It's a crazy idea, I think, from the 70s, when they were decades away of actually making this work. Yeah. Obviously, right, it's very hard to do that because you have exponential blow up, in fact, in 2 dimensions, in data flow and in control flow. Yeah. Because if you are reading 1 byte, yeah, now you're suddenly reading how many bytes or how many configs, right? 256, right? Rather than just 1. And it explodes with the number of digits, of course. Okay. Then also what explodes is the control flow, right? You have a branch, and then you have another branch. If you have a loop, right, you have to unroll the loop and so on. So this symbolic execution is also, it's important to understand that, is a bounded concept. You cannot go on forever, right? You can only explore up to a certain depth. And I'm going to call this depth n. Yeah. So if you look at the execution of the program, I'm always saying that if I start here, this is the initial state of the program, and I start here, and then maybe there's some branches, right? Then what I call n is the depth of the expansion of the control flow of the program. Okay, and it's always going to be finite. Yeah. So this method, symbolic execution, is not going to tell you the guaranteed absence of problems in your code. Right now, it can actually execute your program for all possible inputs and can then find inputs for which you have funny stuff going on, like a runtime exception or division by 0, right? Stuff like this. This is what they use it for. Okay. And the good thing about the symbolic execution is when it finds like a funny state somewhere, yeah, it gives you the input that you have to feed to the program. So, and then it will actually exactly go there. You can validate this and everything. Okay. So people are using this these days already for finding bugs in kernels and Windows device drivers and so on. Right, so this is a big topic. And symbolic execution is actually cool from an engineering point of view because it almost trivially parallelizes. You can, every time you have a node like this here, you can just create another thread and just keep going, right, until you run out of memory. Yeah. So this thing, if whoever has the biggest, or let's say the most amount of cache, can look the furthest into this thing. Yeah. So seriously, some big companies, they utilize data centers for doing this, for symbolically executing highly critical code. Okay. So this is this symbolic execution business. Yeah. I don't have time to really talk about how this works, right, in detail. But there's one thing that's very important to, I guess, to understand is that what's happening here as you're executing this is that you have to basically represent the inputs, right, and keep track of them. Yeah. And what happens here is that as you are doing this, you are creating a so-called Smt formula. Anyone heard about Smt? I'm going to throw a lot of new words at you today. Huh? Smt, it's an Smt formula. So do you know what a sat formula is? Okay, that's our common ground. That's good enough. But you actually don't need to know more than that. So a sat formula, yeah, is essentially, right, it's a formula over binary variables and the logical operators and or not, or whatever universal operator you have. Okay. Now the interesting problem about sat formulas is satisfiability, right? I want to know whether this dang thing is satisfiable or not, any given formula. Yeah, it's an NP hard problem. It's actually as hard as solving these Q-ball problems. Yeah. Now, SMT stands for satisfiability modulo theory. Yeah, so it's a generalization of SAT. Now, the generalization here is that it still contains sort of the core skeleton of a SAT formula, and or not. Yeah. But the variables are now over a theory of something. Yeah. In this case, we are only interested in the theory of bit vectors, which sounds fancy, but it's not. It's just, imagine you have a 64-bit computer, and our bit vectors in this case are 64-bit registers. Okay, one register after another. You know, each is a bit vector. Okay, and now these variables in these SMT formulas, they are variables in that domain. Yeah, they are variables over bit vectors. And now you can, in addition to and or not in these SMT formulas, you can also perform the usual arithmetic. X plus y, x minus y, x times y, and so on. Yeah? But everything is still finite. This is the key here. Everything is finite. So you can ask the exact same question, satisfiability, yeah, for these formulas as well. And if you have a solution, then the solution now is going to be an assignment of variables to their value, right? Which could be a 64-bit value here. Yeah. So the search space here is, of course, much larger, right? It's unbelievable. Yeah. So now in the sort of in that area of SAT solving and SMT solving, people have created fancy SAT solvers that are super fast. They scale, I don't know if you know that, but these days they scale to millions of variables. Millions. This is serious progress, right? When I was a PhD student, this was a joke. I mean, nobody could do anything really nice, right? The machines were too slow and the algorithms were too slow. Okay, so there's an enormous innovation going on there. And that innovation has also translated to SMT formulas, because you can take this SMT formula and actually transform it into a sub-formula, because everything is finite anyway and everything is bits anyway. Yeah. Of course, you will need lots of bits. Yeah. But who cares? We can do millions of bits. Yeah. So there's also the class of so-called SMT solvers that usually in the back end have a sub-solver. Yeah, and then they do something. They take these formulas and translate them down to sub-formulas in a process called bit blasting. Another cool word, huh? These guys are good in coming up with nice terminology. Bit blasting. So you go from here to there to something called bit blasting. Yes. And Stephanie has actually implemented that bit blasting stuff for our paper that we sent within 6 weeks or something. This was crazy, like 3,500 lines of Python code in that time that actually worked. Okay, so I'm going to tell you how this stuff now connects back here to the symbolic execution business. Now, if here, yeah, on this node, there's like a condition in our original program, like if x is less than y, then do this and otherwise do that. Yeah. Now, when I go and create this execution of the program, what's happening is that I'm basically collecting these expressions. Yeah. So that further down in the execution of the program, I know that any value in x needs to be less than any value in y. Otherwise, I'm not going to be in this path. Or it's the false path, and then I just invert the thing. Okay? And then, of course, I also have to keep track of like, operations that I perform. So what I need in my SMT business is basically the theory of all arithmetic operators and comparison operators in my original programming language that led to this program. Okay? That's it. And we have that. Yeah? We have all of this. Okay. Any questions? Are you still following? Yeah, sort of. Okay, so now the first, let's say, key theory, okay, that we are constructing here is the following now. Yeah. So I'm going to say that the formula, the SMT formula that I construct for a given path through this program, yeah, I construct that formula in such a way that it is satisfiable, yeah, if and only if there is an input to the program that will make the program go to that state. Okay, so I have one formula here, formula 1, that takes me to this state. And that formula, if it has a solution, that is a proof that there is an input that the program will take exactly this path. And if it doesn't have a solution, then there is no input that will ever make the program go to this state. Okay, so that's fantastic. So that means I have now, when I translate code to these SMT formulas, I have reduced the problem of symbolic execution to solving SMT formulas, for which there exists really fancy SMT solvers. Like the most famous one is called Z3 from MSR, Microsoft Research. And from my friend who used to be in Linz, so not too so far away, Z3 is from Seattle or whatever, I don't know. Also a good friend, but the other friend is here. And in Linz, the tool that they developed in Linz is called Bulector. Also, it's a competitor with this thing. Okay. Okay. Are you following this? So that we nicely reduce this. Yeah.
Just have a question. Here you say that, okay, I have a path, and then figuring out whether there is an input ending there. This means that the depth n, the depth of the program, or I stop investigating at the depth.
Well, you
meaning
can
that the finite state is really like the finite state of the program, or some intermediate state, but I don't go deeper.
you can go up to here, okay, and the formula is going to be proportional in the length, right? N, the size of the formula, and then you can ask the system, is that still satisfiable? If yes, you can keep going.
Okay.
You make it longer, 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 and if says no, then it's not worth it because there's no input to get you there anyway. Okay, but asking that question whether this damn thing is satisfiable or not is expensive. Okay. All right, so we have done all of this. Now, that of course, this whole question of whether I can go there and there's input for that, I can reduce it. This also reduces to satisfiability, obviously. Yeah. So I have now reduced the question of symbolic execution to the question of satisfiability of subformulas. Yeah. Now I can actually take this here, yeah, and take my subformula and generate a cubo formula that has a solution to 0 if and only if the subformula is satisfiable. Okay, and that's it. So now I can't execute code, C code on the quantum machine like concrete execution. No, I actually do symbolic execution of the quantum machine. And now think about what that means. That means I can suddenly, in constant time, if the damn thing, if the physicists make it work, you know, I can actually execute my program for all inputs at the same time up to a certain depth into the execution of the program. That's absolutely awesome. Okay, symbolic execution in constant time. After doing the translation, and the whole translation, you know, we show that it is actually in linear time, can be done in linear time, and quadratic time if the program does a dynamic memory allocation. Yeah, so it's linear time if the memory consumption of the program is bounded by a constant, and it's quadratic if it allocates memory. Okay, this is more difficult to show that, and we don't have time for doing that, but that's okay. Now, there's one thing that I have been lying about here. Yeah. So it doesn't quite work. There's one thing that wouldn't work like this, right? So you actually, when you look at this, right, how many different paths do you have? How many different formulas would you be generating?
Well, for each path one, so
Yes.
quite a lot.
Quite a lot, right? Actually, exponentially many, right? In the number of branches that you have is a disaster, right? So that's no good, right? How do we do that? Well, we'll do something that actually generalizes symbolic execution, yeah? And it's called bounded model checking. Yet another term. I'm so sorry about this, but it's all cool stuff. I'm not wasting your time, I promise, okay? Bounded model checking. Anybody heard about this? You are a computer scientist, right? I know it's a big field, and I don't know lots about other stuff, so never mind, that's fine. Bounded model checking, okay? So this thing is, in a nutshell, yeah, the intuition is here that with bounded model checking, I can create a model that contains all the paths in one model that is still only linear in size. Okay, but once I expand it, yeah, it can explode. Okay, and there's a very cool format for representing models like this, bounded model checking problems. Yeah. So what we are actually doing here is we generate ultimately a Smt formula that is satisfiable if and only if the bounded model checking model of this thing, yeah, has an input so that the program runs into a state that we are interested in, right? So we actually also solve the path explosion problem through this. So this is also possible, yeah. I don't have enough time to go into the details there, and I think the other intuition that I talked about before was more important to get the idea across, right? So I hope that you actually believe me now that this is possible, right? We can do this. Now, why aren't we, at the end here with, able to solve all these problems and run now? Like, I give you an example of what kind of C program I can write and squeeze through our model now. I can write a C program that checks whether a given Smt formula is satisfiable or not by reading as input the assignment to the variables. It's a verifier, a Smt verifier. It checks whether a given assignment is the solution to a given formula, right? Which is, how fast can you do that? I guess linear in the number of variables, yeah? As opposed to finding an assignment, which is Smt solving and p-hard, right? So verifying is super easy. When you write a program like this in C, you can run it through our tool chain, put it on the quantum annealer, and now what is the program now? That only checks whether an input is the solution of a given Smt formula. It's a Smt solver suddenly, right? It becomes a Smt solver through symbolic execution. Now, if the damn thing solves at constant time, our shaman works, right? The bones are fine and everything. We have, in fact, a polynomial or even a linear time Smt solver. Okay, but only, the theory doesn't let us make that claim yet. Okay, so that's how powerful this is. Yeah, but at the same time, with these restrictions of the physical limitations of all these machines. Okay, so the last thing that I want to I guess 5 minutes, right? And then 45 minutes is the usual here, I guess. 5 minutes is more than enough. Okay, so the second thing I promised to you was the quantum advantage business. Yeah, how can we now show quantum advantage? Well, it works like this. You give me any C program, and I start generating this model here. Yeah, and I will need more and more variables, binary variables, lots of them, thousands of them, tens of thousands, millions. The first versions of the code that Stephanie wrote generated, I don't know, not millions, but quite close to that, for a tiny little program. Yeah. So the explosion is unbelievable, but it's linear, but the factors are unbelievably big. Okay. All right. But now I can, as I'm doing that, I can always ask, I'm on the classical side. Yeah. I can always ask a SAT solver to try and solve the model that I have generated so far for me. And removed all these variables again. I can ask, is it the variable always 0? Is it always 1? I can get rid of it. Yeah. And that actually works very nicely. Yeah? Now I can actually sit down and say, okay, the SAT, I give a time budget to this kind of SAT, asking the SAT solver on the classical side. Yeah. And thereby, within a given time budget, speed of my machine, etc., I can reduce the model, I can minimize the model. Yeah, make it as small as possible. And eventually, okay, I will not be able to solve the model anymore. I cannot optimize it anymore. I will be running out of time on my classical machine. Okay? Once this moment happens, this will also tell me how deep I can look into the code. Yeah? All right? Once this moment happens, I look at how many variables do I need? How many variables are in the model? If the number of variables in the model is less than the number of quantum bits I have on my annealer, I can deploy the model. Okay, and then have the annealer solve the model for me. So now what we did is we defined quantum advantage in the number of qubits that you still have left to use. Or vice versa, it's a positive negative metric. Yeah, you can actually be already past the number of qubits of your machine. That means you have negative quantum advantage by that many quantum bits. Okay, and now the only choice for you is to invest more computational time on the classical side to reduce the model further, so you push it beyond, below the resources on the quantum side. Yeah, so there's actually a connection here between time, classical time, and quantum space. Yeah, and that's something that we defined as a as a notion, a quantitative notion of quantum advantage. Yeah, you can find the paper on arXiv. We put it on arXiv. I'm sure you can read it by now after this talk and see if you understand all this, and also maybe wish us luck. We have sent it to a big conference and we got terrible reviews and from people who have no clue. And well, the notifications on Friday and Stephanie and I are dying, and yeah, well, we can use some luck. Maybe we'll get it in anyway, or do it some other place. Then. Thanks a lot.
Any questions, comments?
Yeah.
I'm interested in the quantum side. Let's say if you could tell us more about. Is it so that the variables correspond to the state of the qubit, right?
Yes.
And what does the cost function correspond to? Is it Hamiltonian or energy or?
No, this is the function that we generate so far is only a quadratic function, and it's only meant to program a quantum annealer. Okay, so we don't need to deal with unitary matrices and so on. Those are for gate model machines, and we have not targeted them yet. but we are currently actually working on this. So our tool chain, we developed the tool chain. It's now beautiful already, written in Rust and everything, very fancy. And we are working on two different targets, for this tool chain. One is quantum annealers, and for that we have to do a quadratic model. And for the gate model, we are going to generate a circuit, quantum circuit.
Yeah, I could imagine the circle, but I'm trying to find out how does the actual computation work. How do you hard code the cost function, the cubo in that?
Yeah, I don't know yet.
And what you receive after the computation, because you have to measure it at the end. Is the result with some probability? Is the result the actual solution or the actual?
In our case, this is a good question. In our case, even on the gate model, a solution would be an input to the program that takes you to a state that we are looking for. Yeah, so we always encode in the formula a description of the states that we are looking for. Like, yes, this formula is satisfiable, or yes, here's a division by 0 for debugging, that kind of thing. So even the gate model machine will return one possible input that then leads to this particular state in the original C program. Yes. But the question, you see, what we are currently doing now is we are targeting the gate model because it's interesting, even though machines are too small, that doesn't matter. And also what we are studying is even one more, like we are trying to take one step further by asking what is the kind of program that using this methodology here will give us an exponential advantage guaranteed. Yeah, because some algorithms on gate model machines have an exponential advantage. And we want to show that we can actually also utilize this through our tool chain. But that's ongoing work.
On the gate model, usually the concept, which is standard, is that you start with all possible inputs and you perform something so that most of them cancel, so that you receive the correct result. But yes. I believe this is something different, because you are using the SMT things in order to so that you don't have to start with all the inputs. You just start with some, I don't know, perhaps random, and you let the adiabatic computation do the work.
Yes, but we are not starting with any random inputs. We are not even trying to solve the model. Okay, we let the adiabatic machine do that, yeah, for us. But we can always ask an SMT solver to find us inputs, right? It can solve some of these models, of course. But the method that these SMT solvers use can be all kinds of stuff. They start with random inputs and then explore the search space and so on. All kinds of things are possible there. But we are not actually working on this. We are basically, this whole thing here that we are doing is basically just translation. And the challenge is to not introduce exponentials in the translation. But eventually, of course, we want to show not just quantum advantage, we want to show exponential advantage that is guaranteed. But this is what we are doing right now, but this is, of course, hard. It's not clear how to do this with our tool chain. Yeah.
You mentioned that the quantum annealers, they're not universal.
Yes.
So what is some example of problems that it can solve?
So now, after this talk, was a good question, is you can see that, because this thing can only solve functions like this. So it can only run the program up to a certain n. It cannot keep running. And that's really in a nutshell, the difference. Whereas in a gate model machine, I can take this model and put it on a gate model machine, and there is no n involved here. And the difference is also another response to your questions is that if we put our model on the gate model machine, it's going to be for all n. Okay, that's the difference. Yeah. But you know, it's really not. I mean, there's a lot of work here necessary in optimization and so on, because we are using way too many quantum bits. Right? There's no chance you can actually put this on a gate model right now. So there's lots of. I mean, it's just a paper factory now, right? So you just write papers one after the other to actually make it eventually work, I guess. You know, and maybe some of you are interested in helping us with optimization issues and so on.
So you just out of curiosity, because like the Cubo model looks pretty simple. So if you have like if any SMT formula can be translated into Cubo, or is there some limitations? There are some SMT formulas that you can't?
No, it's well, you have to be careful, right? SMT stands satisfiability modulo theory. So the theory can be anything, right? Any decidable theory. Yeah, the theory of floating point numbers. I don't know, crazy stuff, complex now, whatever you want, right? So, but at least for bit vectors, finite bit vectors, yes, you can any SMT formula over that theory can translate it to that.
We translate it as just about number of variables.
Yeah, it's just you know,
Okay.
yeah. It's all. This is all called bit precise reasoning. Which is awesome, right? Because when you actually want to use this stuff, you don't have to be a logician or something. The specification of correctness here, if you want to use this to verify your program, then the specification of what you're looking for is very simple. These are mostly safety properties. So you just say, I just want to know if the program ever divides by 0 for any input. That's it. You don't have to write a fancy temporal logic formula or whatever, or you know, it's all bit precise reasoning, and it's nice in practice also because it gives you the witness, it gives you the input, and then you can run it. That's why Microsoft, I think they choose not to open source that 3, because they don't want people to find the bugs before they find it. Because this damn thing is like the hacker's dream, right? It actually gives you the payload that you have to inject to exploit whatever, right? It's fantastic. You can even be a not so well informed hacker and still do it. Yeah, it's awesome. So these tools are critical. Yeah. Yes.
You said that these quantum annealers give you correct answer with high probability. These quantum annealers
Yes.
gives you correct answer with high probability.
Yes.
Is there any guarantee on this?
No.
Probability? No.
That's the problem. Yeah. So I don't know what's wrong with these physicists, right? They need to. This is I'm a software guy, right? So I just want better hardware. Come on. And then we can do great stuff with this. Yeah, but I don't know if you realize this, that a long time ago, the programming model of digital machines was also not so clear, right? I mean, it was a non-obvious thing in the 50s or something, yeah? And now we are in an era where we have the same problem again with quantum machines. What is the model? How do you actually program these things? Yeah, and make it accessible to lots of people. And I think our tool chain and this idea is a bit of a contribution to that, because now you can at least see the connection, right, between these two worlds. So we need to develop programming models to interface our software world to the hardware world, so that we don't have to understand all the physics of the quantum machine. Just like, I don't know, most of us here, I guess, are there any hardware people here? No? So I can speak candidly. We don't have to understand how the transistors work, right? Most of us, we had to take classes about it. It was very painful, blah, blah, blah. But But in the end, we can forget about a whole large portion of physics and still do our job. And with quantum computing, it has to be the same thing, but we actually still need to do the work, right? This is not done yet, right? This is an ongoing conversation. Yeah. Right.
Okay, any further questions? If not, then let's think again. There is still some more pizza.
How the simulation really collects that. That's pretty cool. But then the question is, so how big this program is? If you have a program that will try to figure out whether that is a solution program, how big is the program? How can you figure
So that we basically now we just deal with the core, right? But you write in the experiments, we are not there. But we are the person that's cool. If we don't get this into PLDI, right, it sucks.
Yeah, but it would be great if you start the abstract with this, and then
yeah, I can do a different skill, but I was expecting to do this. He's written why they didn't give it to him.
that's bizarre.
He had the quantum paper last year. What stage? It's a big deal.
Yeah, but if you read that one, that was that was much lighter.
Yeah. I did.
Yours is very condensed. But I guess if you would turn it the other way around and you start with this, so everyone understands the coolness, then because I guess in the end really I guess the catching the attention, right? That people will figure out if this makes sense and there's no logical error, but
So you mean starting with this?
no, even later. This how the symbolic execution is collected and what you can do.
Yeah, and how would you start the paper? With this or with this?
No, it's very at least I didn't understand it.
But you now understand?
More than before. Now I can solve it. It's very good.
Is there something on it?
No, she's just proving that she has no limits. It's all recorded by her.
Oh, okay. Yeah, be careful. Be careful. Okay, let's go.
Let's go for years.
No.